Under this teaching, we'll be dealing on laws of logarithm. This is the second teaching under logarithm. The first tutorial, about 20 minutes class, was dealt with definition of logarithm with basic examples that justified the definition. All right, so you have to watch that very first tutorial before you be able to follow along with these ones. Also try to master the laws of logarithm of indices. The first 5 videos on my YouTube channels dealt with indices, so you have to master them very well before you'll be able to follow along with logarithm properly. All right, now having said that, the laws that we have to treat here is we have product law, we have quotient law, we have power law, we have base changing law, we have reciprocal law, and then we have some special logarithms, which has to do with a logarithm of a number to its own base, okay, as well as logarithm of 1 to any base, okay. All right, now we now deal with a product law. Now we say this states that the logarithm of a product of two positive numbers is the sum of the logarithm of the separate numbers, okay. Now let's say if you have logarithm of product of two numbers which to base a, it is equals to logarithm of those the sum of those two is equal to the sum of the logarithm of the separate numbers. So this is the first number, this is the second number, that's m and n, okay. Each of them will take their own logarithm and base. Instead of multiplication, we now deal with plus, just like we deal with indices, okay. Now, but for quotient, the difference between quotient and the quotient and this product rule is that instead of plus, we now have what? Minus. So we say logarithm quotient law says that the logarithm of a quotient fraction, quotient is same thing with fraction, okay, is the difference between the logarithm of the numerator, okay, and that of the denominator. So here, this is the logarithm of m over n. So if you try to give each of them their logarithm, you instead of division, we now deal with what? Minus, okay. All right. Now power law says that the logarithm of number n raised to power of p is equal to p times the logarithm. So that means the power multiplies the logarithm of the number, okay, of the number. So we now have, if you have logarithm of n to the power of p raised to the power of p to base a, is same thing with this p multiplies the logarithm n to base a. So the only thing there is that this power multiplies the logarithm. Okay, now I have to explain the laws. Then we can now cite examples each under this tutorial. Now, base changing law is the next one, which is the logarithm of a number b to a base b. Sorry, the logarithm of a number n to a base b is equal to the logarithm of the number n divided by the logarithm of the given base. Okay, now all to the new base a. All right. In some cases, it is expected that we change the base. So what we do is logarithm of n to base b. Some cases, if you equate this to x, you won't be able to get raise b to power of x to give us the n. Okay, so you understand better when we deal with examples. So in this case, if you have to change the base. If you want to change the base to justify whatever variable you want to assign to it, you have to, if you change the base of this to, let's say a, the first will be logarithm the base a, logarithm of n to base a, all over logarithm of that same new base that you brought. Now this b, which is the base here, will become the number for this one. Okay, so the new base is just a introduced. So this n is the number here, and this b is the number as the under the denominator, So here we have another law, which is reciprocal law. Now the logarithm of a number n to a base b is equal to the reciprocal of the logarithm by interchanging the number and the base. Okay, now if you have logarithm of n and b, in some cases, you know, it will not be possible for you to also work it out directly like that. So what you do is to find it to be solvable or workable if you want to do the get the inverse. So here I'll have 1 over logarithm b base n. So once you put that reciprocal, which is 1 over, okay, another word for reciprocal is inverse. Okay, 1 over is the reciprocal here. Once you do that, this number of logarithm become the base, and this base become the number. That's what we mean, interchanging the number and the base. Okay, all right. Now, special logarithms. Logarithm of a number to its own base as the number is equal to 1. Okay, that's when the logarithm of a number have the has base the same as itself, and whether it is equal to 1. Okay, now this is how to justify it. Let's just say from the previous example we've been dealing with in other tutorials, we assign x to the, assuming we want to look for logarithm of a base a, we just assign x as the variable and start looking for the value of x, which will be in turn be the value for this logarithm 8 base a. All right, we now have a we take this variable as its power equated to this a. Okay, of course this a is sent to with a raised to power 1. I have to extract the power so that I'll end up cancelling the bases. Once I cancel the base at this point, I will equate the power, so s equals to 1. In other words, logarithm of a to base a is equals to 1. Now the next one is logarithm of a number 1 to any base equals 0. So anytime you have logarithm of 1, whatever base it is, it will equate it to 0. All right. So now the at this point, I'm dealing with examples of examples on the laws that I just did now. Each one example for each. Now, before then, in the next tutorial, we'll now deal with multiple of the laws combined. Okay. Now we have product law. Here we have log 5 plus log 20. Now you'll be wondering, how can this is this actually product? No. In some cases, it will come as in form of product. In some cases, it will come as if it is a addition. So whether it is addition or multiplication, the product rule affects it. Okay. Now, if you have logarithm of 5 plus logarithm of 20, and you know that there's no way you can work on this to get a single value, a number, and also work on this and get a number, just apply that law. You apply it on the other way around, which imply that you take one of the bases and then multiply the numbers. So you factor out the log, okay, not bases, okay, just factor out the log and then multiply the numbers. That 5 times 20 equals to log 100 now. Okay, now of course log 100 is equals to log 10 raised to power 2. 10 raised to power. The reason why we have to extract this 10 raised to power 2 is because we know that, just recall that anytime you're not giving base, it is automatically having base 10. It is assumed to have base 10. Okay, so in other words, in this case, we have logarithm of 10 raised to power 2 to base 10. And of course, you know, one of the laws stated that we have that logarithm of a number to its own base is equal to 1. Okay, you can go back, you can just go backward and recall what I just said under those laws. Now, since we know we have 10 here, we can take, of course, power law also implies that we should use this, we should take this this power multiplies this log. So we now have this 2 multiply the log 10, okay? And then logarithm of 10 to this automatic 10 here is equals to 1. Logarithm of a number to its own base is equals to 1. So 2 times that 1 is equals to 2, okay? That's just it for this one. Now, we have quotient law. Now, quotient law, under quotient law, example is logarithm of 8 over 4 to base 2. Okay, now in this case, we can have logarithm of 8 to base 2, as in share each of them their logarithm, and then instead of division, we have what? We have minus. Now, why didn't we just assign x to it and start solving? I think if we do it that way, I don't think it will be possible for us to get the answer, but peradventure it is still possible. This one is still justified, okay? It's more justified. So here, of course, we now have, if you want to know the one to apply first, just with your initiative, mathematics is all about thinking and reasoning. So here we have, that when the 8 have base of 2 here, there's a way you can get 2 raised to the power something to give you 8. And there's also a way you can get 2 raised to the power something to give you 4. Of course, 2 raised to the power 3 will give you 8, and 2 raised to the power 4 will give you 2. 2 raised to the power 2 will give you 4. So since you're going to have 2 here and 2 here, and also 2 here raised to the power 3, that's 2, 2. Of course, you recall that 2 logarithm of 2 to its own base 2 will give you 1. So you just have to apply that initiative in order to make things easy for you. This way we have it 2, 2, 2, 2. Okay, so we have 2 raised to the power 3, of course, is 8. 2 raised to the power 2 will give you 4. All right, still with base 2, 2. Now, at this point, we apply that power law, okay, which is the power idea multiplies the log. That's 3 times log 2, 2. And then these two multiply this as well, 2 times 2 base 2. Okay, now we now have logarithm of a number to its own base is equal to 1. Logarithm of a number to its own base is equals to 1. So 3 times 1 is 3. 2 times 1 is equal to 2. Now 3 minus 2 is equals to 1. Now under law, under power law, we have under example to justify the power law, we have 81 raised to the power x over y to base 3. We have of course, in this case, we can still extract the power here at this point. That's 3 raised to the power 4 to multiply with 4 taken over, or you still work it out respectively. That's one after the other. Now you can just consider this power law, okay? Take the power over, okay? And then what you have next is logarithm of 81 to base 3. And now at this point you have 81. Look for a way to make the base and the number the same. That's, of course, 3 raised to the power 4 will give us 81. So we have 3 raised to the power 4 here. Now, of course, this one and this one will end up giving me 1 if I remove this power of 4. So I have to still remove this power of 4. And then when the power of 4 is coming over here, it will still multiply, okay? So multiplying this s over s, it will multiply this s over y. Okay, we still have log 3 base 3, okay, left. So, of course, 4 times s is equal to 4s, then we have over 1. 4 times s over y is equal to 4s over y. Okay, now logarithm of a number to its own base is equal to 1. So this multiply the 1, still giving us 4s over y. Now, this other one says, under base changing law, we have, this is the law that we stated there, that when, in some cases, you won't be able to solve it out just directly. There's no way you can erase a to any power to give you this m. So in that case, we have to apply this base changing law. Or even if you, okay. Now in this case, we change the bases, and once you change the base, that's bb to which was never in the question. Just use another value for the base. We now have this number m will become the number for this, and this base will become the number for the denominator logarithm. Okay, now we have a question here. We said prove that log 4 base 3 times log 5 base 4 times log 6 base 5 times log 7 base 6 times log 9 base 7. Okay, this is base 7. Okay, this is base 7. All right, is equal to 2. That we should prove that everything here is equal to 2. So that means we have to ignore 2 here and then carry everything here along, and our answer must give us 2 if the question is actually correct. All right, so we have logarithm. If you look at this, you find that there is no way you can make the base and the number here the same in order to factor out and then have 1 here. Now, even if you cannot do that, what about applying multiplication law? We cannot apply multiplication law here, because the reason being that each logarithm, each term here is having its own logarithm. So had it been they were having plus or plus plus, we cannot extract the logarithm, but since it is times and they are still having their logarithm, it is still not possible. In other words, we can now apply that base changing law. Okay, now we have in this case, it is advisable for you to take the smallest base here as the common base for all of them. Just change every base here as to be 3, and once you change it for this one as logarithm 3 base 4, that's you are using 3 for this 4, and you also use 3 for this 3. So we now have logarithm of 3, that's of course divided by this same 3, that's BB. We also have 3 that we changed. So that's logarithm of this 3 now will now become the logarithm number to base the new base. Now we now have logarithm of, instead of 4 now we still have 3, okay? Now to base 5, and then log 3 also to this base 4, okay? Sorry, this 4 now become the number. The same thing happens here. Logarithm of 3 for all of them. Now 6 becomes the number here, 5 becomes the number here, 7 becomes the number here, 6 becomes the number here, 9 becomes the number here, 7 becomes the number here, all in base 3. Okay, now that we have done that, we find out that there's something common between this. Okay, once you finish doing this kind of law base changing, it is possible for you to start having common things to cancel out. Of course, this is the same thing with this, and this divide this will cancel out, this divide this will cancel out, this divide this will cancel out, this divide this will cancel out. Okay, now this one doesn't have anything to cancel, so the only thing left here, of course, everything here is 1 1 1 1 1 1 1 1. So 1 times 1 times 1 times 1 times 9 times log 9 base 3 is equal to log 9 base 3, and log 3 base 3 times 1 times 1 times 1 is equal to log 3 base 3. Okay, now of course we know that logarithm of a number to its own base is equals to 1. And look at this one, we also know that it is possible for us to bring out 3 here, so that we have logarithm of number to its own base. So 3 raised to power 2 give us 9. So we now have to apply power law here. Taking this power over, we have 2. Okay, this 2 multiply this will now multiply the log. Okay, of course anything over 1 is still itself. So logarithm of a number to its own base equals to 1. So we now have 2 times 1, okay, equals to 2. In other words, it is proven that everything here is equals to 2. Okay, all right. Now reciprocal law. Now under reciprocal law, we have logarithm of 8 to base 2. Now in this case, you find out that, assume, for example, assume I have something like, let me do it. Let me correct out here. If I have this log base 2, sorry, log 2 base 8, and I want to solve it like ordinary logarithm, like we did before. Of course, the first thing is to assign to x, and now we have this base. We take this number as its power. We have 8 raised to power s equals to 2. Now we ask ourselves, can we ever make the base the same at this point? No, the answer is impossible. So since we cannot, okay. All right, here it is possible we can still have 2 raised to power 3x equals 2 raised to power 1, which is sent with 3x equals to 1. Okay, so of course dividing both side by 3, we have 1 over 3. That means dividing both side by 3. 3 will cancel 3, so we have 1 over 3. Okay, now in this case, we still apply the, instead of using this method, we can still use the reciprocal law, which is of course, which is still going to give us the same answer. It will not contradict. Okay, all right, 1 over 3. So here we have 1 over this 8 here now becomes the base. Of course, when you have reciprocal, from the law that I stated before, I said the two of them will interchange. So 8, which is the base, becomes the number. 2, which is the number, becomes the base. So here we have 2 raised to power 3, and this 3 will multiply. 2 raised to power 3 is equal to 8. 3 will multiply this to give us 3 log 2 base 2. And logarithm of a number to its own base is equals to 1. So 3 times 1 is equals to 3. That's 1 over 3. Just like we have here, 1 over 3. Okay, it is justified.